A problem that we encounter is the vertical spring problem. And the takeaway is that vertical springs are just like horizontal springs if you measure the stretch or spring compression from the what we'll call shifted equilibrium position. So we'll look at this with an example where we have a spring with a spring constant 250 newtons per meter hanging from a fixed ceiling with a 10 kilogram pan attached to the other end. And we'll place a 15 kilogram object in the pan and release from rest. And we'll be interested in finding questions like the downward displacement, the maximum downward displacement that the pan will go. After all, a mass and spring obey simple harmonic motion. So when we release the 15 kilograms into the 10 kilograms, the combined 25 will cause the spring to stretch. The 25 will fall. But as the spring stretches, it will slow down, turn around, and spring back and continue to oscillate. So we'll get that maximum displacement down. We'll also get the frequency of the simple harmonic motion. We'll look for how much time it takes for the pan to go from its initial position to that lowest point. And then we'll find the average speed of the 15 kilograms from when it's placed in the pan to when it reaches its lowest point. Now, we have the vertical spring with the 10 kilogram pan, and the 15 kilograms is on the side here. But before we deal with that, let's realize that the actual spring was at its equilibrium position when it had no mass hanging on it. So already the 10 kilograms has stretched the spring. And that's what I want to look at. I'll look at a y-axis that shows the zero, or we'll call it the equilibrium zero, the equilibrium position, which is the true unstretched spring. And we'll just call that point zero. It is from there that we measure stretch or compression. But with the 10 kilograms, or here I'm just calling it M now, M has stretched the spring a distance x. And if that M was put there and allowed to come to rest, we would have equilibrium between the downward weight and the upward spring force, right? mg equals kx, where x is s. And I'm ignoring signs. We just have a balance of forces, right? The upward spring force is being balanced by mg. And what I'm suggesting here is that consider an x-axis where the 0 point, the point from which you measure stretch or compression, the 0 point now is the mass that's at rest. We'll call that EQM. EQM is the shifted equilibrium position, and we're just calling it 0. Now, from a force perspective, we would have, in terms of our y components of forces, the spring force minus ky. Now, y doesn't have to be negative s, right? S below 0. Any y value minus ky is the spring force. And then we also have mg down. And it's interesting to see what that looks like in terms of x. Now, x minus s is y. And you can convince yourself of that if x is a distance x away from 0, right, then that's when y is 0. So we can get this condition from the s that we found just by comparing the two origins where y is 0 and where x is 0, and realizing that while x minus s has to be the y value, right? Again, when x is s, y is 0. So you can verify this equation. In any case, let's get the force in terms of x instead of y. So I have minus ky, which is x minus s. And then I have my minus mg. Now I have minus kx plus ks minus mg. But notice that ks minus mg is 0. So I get my spring force is just minus kx. In other words, the spring force is the same that you would have if the spring was horizontal. We're just measuring x from the shifted equilibrium position. Now we can get a similar conclusion from an energy perspective. The potential energy of a spring, a mass and spring system at this location with this choice of 0, right? We would have 1/2 k y squared. Now the ground for MGH is arbitrary, but if I just use the 0 that's here in the y-axis, I would have plus mgy, right? When y is below 0, negative, we have negative potential energy of gravity. When y is positive, positive, so this works. But again, we have that x minus s is y, and we'd like to get the energy in terms of x. So my potential energy is 1/2 k y squared, which is x minus x squared, which is x squared minus 2xs plus s squared. And then I have my mgy, which is x minus s. So mgx minus mgs. Right? If you don't like derivations, the takeaway is that we treat the vertical spring the same as a horizontal spring, and do not include the force or energy associated with gravity, provided we're working from the shifted equilibrium position. So again, with a little derivation, I just want to get to that point. I have my 1/2 kx squared. Now, I have 1/2 k minus 2xs. The half and the 2 cancel. I have minus ks times x from this middle term. And I want to combine that with this term here. I guess it was this one, right? Because ks is mg. So the 1/2 k minus 2xs, which is minus ksx, is also minus mgx. With the plus mgx, those terms cancel, right? And now what I have left is 1/2 ks squared and minus mgs. And I can manipulate these a little bit more, but the point is they're constants. And since they're constants, they don't change in the problem. Another way of saying it is with another choice of ground for the gravitational potential energy, I could just as well have made that constant 0 arbitrarily. And so the issue is that since energies, it's usually only changes in energy that matter, we're getting that the energy that we would have to deal with is the same formula, 1/2 kx squared, that we would have had with a horizontal spring. So again, a vertical spring, where we have both spring and gravitational potential energies, we can say, no, we only have spring energy, no gravitational potential energy changes, even though it's going up and down. And the reason that works is we're measuring the stretch of the spring from this shifted equilibrium position, right, that we called EQM or EQ shifted, as opposed to EQ0, the true equilibrium. All right, so this slide and the previous slide was just to derive that we can treat vertical springs like horizontal springs if we measure stretches or compressions from the shifted equilibrium position. Now back to the problem at hand. So we place the 15 kilograms into the pan, and now we let go. And the thing is, when we let go, we actually just need to consider some of these equilibrium positions, right? We have the true EQ0. We have the EQ10 for the 10 kilogram pan. But what we're after is EQ25. And EQ25 from the original problem is an additional shift D based on adding the 15 kilograms. So we can say 15 times 9.8 is the weight, the additional weight down is balanced by an additional spring force up, K times the that additional distance D. Right now, K was given in the beginning of the problem as 250 newtons per meter. So we get D, the shift from the beginning of the problem to this, what essentially is the shifted equilibrium position for the simple harmonic motion, comes out to be 15 times 9.8 divided by 250, 0.588 meters. Now, notice then that the 0.588 meters, after all, the motion is simple harmonic. And if we release the 25, the 15, and the 10 at rest, that's an extreme point of the motion, right? This object will continue to oscillate up and down between 2 points that are at rest. In other words, just by understanding the motion without actually having to do an energy balance that would have been horrible if we had to start measuring from here, heights and stretches, we can just say that this is the amplitude of the motion. So we get another one on the other side, right? The simple harmonic motion is oscillation about plus and minus an amplitude. So in other words, we get the displacement magnitude, or the displacement down, delta y, from initial released, goes down, turns around back, and springs back up. We get that full delta y as twice the amplitude that we found by inspection, basically. So that gives us 1.176, 1.1, let's see, that was 1.176 meters. And so if we go back up here, actually here, we have our maximum downward displacement just by considering an equilibrium position with the 25 and realizing that the motion happens about that point. We pretty much, without much math, just a little understanding, get the 1.176 meters maximum downward displacement. Now, for the frequency of the motion, we would get the angular frequency. This is one of our formulas on our formula sheet. The angular frequency of a mass on a spring is the square root of the spring constant over the mass. And it's the whole 25 that counts. So we get square root of 10, we get 3.16 radians per second. Again, look at the formula sheet in the files folder in Canvas. Frequency is omega over 2 pi. We turn radians per second to cycles per second by dividing by 2 pi radians per cycle. And that gives us a frequency of 0.503 cycles per second, or hertz. So this was B, this was A. And then for C, the time required, well, coming all the way down and back is a period, right? A cycle. Now the period is 1 over the frequency. And that gives us a period of 1.99 seconds. So if we're just looking at the time required to go down, that's half a cycle, right? We went from one extreme to the other, from peak to trough. And then coming back up to peak finishes a single cycle, right? So this must be the time, twice the time we're looking for. So the time we're looking for is actually half a period, and that is 0.993 seconds. And last but not least, D is to get the average speed as the distance that we found over the time that we found, and we would get the average speed to be 1.18 meters per second. So again, the key to vertical springs is to treat them like horizontal springs after you realize where the equilibrium position is located. Again, if we did not do that, we might have thought to find the true equilibrium and realize that we have spring potential energy, initial and final, which is at that level, and plus have gravitational potential energy, both initial and final. And if you were to try to do an energy balance, conservation of mechanical energy, you would have lots of terms, and you would end up needing to solve a quadratic equation. And we did this problem in class, but again, for this video, the takeaway again is that vertical springs are basically horizontal if you find the shifted equilibrium position and count only the spring force or energy from that shifted location. Okay, that's that.